You may be wondering, why am I sitting here in this awesome chair that Daniel built, blowing bubbles? What does that have to do with a calculus lesson? Well, actually, it has a lot to do with calculus because if you think about that bubble that I'm blowing, it has a volume that keeps growing. And when the volume of that bubble grows, it's pretty basic math and science to say that it would be growing at some rate. Would you agree with me? The volume is growing at some type of rate. Now, the other thing, if you think about a bubble growing, it would have a radius. Now, this is a little harder to imagine, but can you kind of see like a little radius inside of that bubble, inside of that sphere? Well, that radius would be growing also, right? The radius would be getting bigger. So the radius also has a rate. It's changing by a rate. Now here's the big question of today. How are those two rates related? How is the volume getting bigger related to the radius getting bigger? Now you would have to agree that both are getting bigger, but are they getting bigger by the same rate? Just ponder that for a moment. If you say yes, you have to realize that the volume is a cubic. It's a three-dimensional rate. The radius, that's a linear, that's a one-dimensional rate. So it can't be true that they are the same, but they're related, right? If the radius grows faster, the volume's going to grow faster. If the radius grows slower, the volume's going to grow slower. Well, instead of just using our hands or using the words fast and slow, it's probably not a surprise to you that we're going to use derivatives. That's right, derivatives are going to show us how the rates are related. Here, let me show you.
Now, before we can use derivatives to determine how the volume rate and that radius rate are connected, we're going to need a formula. And of course, we'll need a formula that involves volume and radius of a sphere. Actually, backing up maybe just one more second here. This is lesson 4.6, related rates. And as I always tell students, it's really the last lesson on derivatives. And maybe that's good news to you. But for me, it's good news because it's finally the lesson where you get to really see what really is a derivative. And I hope you conclude it's a rate. It's actually been a rate since day one, but today you're going to see how it's a rate in an actual application problem. It's a pretty neat lesson. So are you ready? We're going to take a look at the sphere volume rate problem. This is a sphere. I called it a bubble a few minutes ago, but it's really a sphere. And we're going to look at its volume, the rate of the volume. Now, we need a formula that uses volume of sphere. As I have said before, when we do these problems that require formulas, the purpose of the problem is not to have a formula memorized from geometry, but more importantly that you say, all right, I need a formula that uses volume of a sphere and the radius sphere. And from geometry it is 4/3 pi r cubed, and of course you could look that up or find it if you needed to. Here's the important thing. Are you ready? If we're going to do a derivative of this formula, but we're going to do it so we can get a rate, what you're going to find out is that we need to do the derivative with respect to time. Now, with respect to time, maybe you say, what do you mean with respect to time? But you're going to find out that means that we're going to get a new variable in this problem. It's called dt. And dt means the derivative with respect to time. Now, it's just one of those things that I need to show you. I need to show you for the first time. We're going to show you another time. Eventually, you'll get the idea of how we do the derivative with respect to time. So, you ready? We're going to do the derivative of v. Now, the derivative of v is 100% dv. But when we do it with respect to time, it's going to be dv dt. All right, now I'm going to say a little bit more about that in a second, but let's go over here and let's do the derivative of the other side. Because over here, I actually have, honestly, just kind of a fancy coefficient. 4/3 pi is a coefficient, and since day one of derivatives, coefficients have always just come along for the ride. So don't forget about it, but don't change it. We get 4/3 pi. Now, it's the r cubed that we're going to need to do the derivative. And I'm going to submit to you that we're going to need to do the derivative like a chain rule. Now, the reason we need to do it like a chain rule is so that we can end up doing the derivative of the inside. Of course, first, you have to do the derivative of the outside and leave the inside alone. As you finish the derivative of the outside, we get to the second power. But as I was saying, we're going to do this like a chain rule because now I'm going to do the derivative of the inside. Can you guess what the derivative of r is? That's right, it's going to be dr, but dt. Now, dt means we're doing the derivative of these variables with respect to time. Now, what it also means is that dv dt actually represents the change in the volume over the change in the time. And in a similar fashion, dr dt means the change in the radius over the change in time. Kids, those are rates. Whenever you have a derivative, whenever you have a change with respect to time, it's a rate. Let me encourage you to take what I said there verbally and really process this. A lot of students will circle both of these fractions so that you can perhaps record that dv dt is the change in volume over the change in time. That means it's the volume change rate. And then the change in, and then dr dt, which is the change in the radius over the change in time, which is the radius change rate. Now, if we go back to our derivative, it turns out that we can do a little bit of simplifying. And, well, anytime you can simplify, you should. It's certainly going to make this problem look a lot easier, because really this divided by 3 and this multiply by 3, yeah, they're going to cancel. And so if I just cancel those 3's and perhaps write this one more time, I get dv dt equaling now just 4 pi r squared dr dt. And what you're going to discover is that this is really the formula that relates those rates. Remember when I was blowing that soap bubble, we were trying to figure out how does the change in the volume relate to the change in the radius? Well, here they are. They are related by this formula 4 pi r squared times the change in the radius. So the cool thing about that is when you get a formula that actually relates the rates, then you can plug into it and find your unknown value. Let's pretend that we were actually able to measure some things about that soap bubble. If you look at this kind of hypothetical here, at what rate is the volume of the soap bubble increasing if the radius is currently 6 centimeters, but it's growing at a rate of 3 centimeters per second. Do you see these two values? Do you see how they can be plugged into our formula? The cool thing is that the volume rate, that is dv dt, is simply going to be 4 pi times the current radius squared, and then times the radius rate. And so we end up with something that obviously can very easily be put into your calculator. I encourage you to do that, or if you just kind of want to follow me and you trust here, if you multiply this all out, you end up with 1,357. Now, 1,357, that's actually a volume rate. And you're going to find that actually I'm a little picky about your labels. So I always want you to label your rate. And since this is a volume rate, it's going to be centimeters cubed, but per second. And again, I'm actually going to ask you to write the labels of your answers just so you can show yourself that you understand that you found the volume rate. By the way, 1,357 centimeters cubed per second, that is a very different rate. That is a very different rate than 3 centimeters per second. So obviously the two rates are related, but they're very different types of answers. Now, what we just went through is your first example of related rate problem. And I'll share with you that there's definitely more to these problems, but there's not less. So let's keep going. We're still kind of young in our understanding. It turns out that a lot of these problems, they're going to require quite a bit of setup. They're going to require quite a bit of organizing and ultimately understanding before you even get to the part where you're going to do the derivative and plug in for your final answer. The book has a 6-step strategy. I honestly believe that all those steps are important, and I encourage you to look at them. But these 3 steps in the middle, they are the key steps. They're the ones that really are the organizing and setting up of the problem. It's so important that you may even, I encourage you actually to pause the video right now and even jot these down, because I'm going to be referring to these 3 steps and just looking at them, writing them down. That's probably your first step in getting a little more understanding of these related rate problems. So pause the video, jot these down if you choose. And although they're not going to make perfect sense until we start doing the next problem, let's just kind of want to highlight number 2 here. You're going to interpret numerical information as calculus value. That's going to involve assigning the correct DT symbol to particular numbers that are given to you. Step 3, identify what you got to find. It's actually going to be the same thing. You're going to be trying to assign the correct DT. Now, if you're like, what do you mean assign DT? Well, we're going to be using symbols to basically label our numbers. And then the last thing is coming up with the right equation. What you're going to discover is that the equation has to use the variables that you've already kind of labeled and classified in steps 2 and 3. Now, I'm going to be using this helper paper to make it a little easier for us to follow along with each of these next applications. So the next one we're going to do is going to be the draining can. Basically, it's number 1 here on our paper. Take a look at it, read it once, read it twice. How fast is the water level dropping when 5 centimeter radius cylindrical can is drained at 30 mils per second? Picture a soda can. It's got liquid in it, but there's a hole in the bottom. And so obviously the water level is dropping. And we're also losing a certain amount of water, a certain amount of volume every second. So let's see if we can figure out how to find that changing height. Now, to do this, what we need to do, according to this little strategy, is try to interpret what we're given as some calculus values. Do you notice, I'm sure you do, that we're given 5 centimeter radius? Well, that really just means that the radius is equal to 5. I know, pretty simple stuff, kind of organizing what you're given. But do you also see that we're given 30 mils per second? That is, that it's draining at 30 mils per second. Now, here's our first time or our next time in this lesson where we're going to try to interpret something like a rate. You got to see that if we're draining at 30 mils per second, that's a rate of draining. It's a rate, actually, of volume. So it's the change in the volume over the change in the time. It's dV dt. And how is the volume changing? Well, it's changing by 30 mils per second. Now, it's losing 30 mils per second, so we have a little added piece to this. That is that it's going to actually be a negative rate. Yes, you can have negative rates. They just describe rates that are going down, or in this case, like you're losing. Now, that would be considered step 2 in our little strategy, but we also have a step 3 that honestly kind of blends into this, basically still trying to organize and get things set up. I'll tell you what, I'm going to write that up here. And so now what we want to do is we want to think about what we're trying to find. We're trying to find how fast the water level is dropping. Now, that would be like the height in that can. Okay, it would be the height. But more importantly, I want you to realize that it's a height rate. It's the rate that the height is changing. What does that mean? That means that we're trying to find dH dt. dH dt. It's the way that we describe that height rate. All right, and well, as you can see, once again, it used dt. Okay, lots of the parts of these problems use dt because they're rates. Now, finally, step 4 is to come up with an equation that's going to use these variables. Now, here's the cool thing. We've already done the hard work of realizing that we've got a radius, that we have a volume, and that we have a height. All we need is a formula that uses those 3 variables. Now, it's going to be connected to the idea that this is a can, and so we don't have to go searching long and high and far for a formula that involves the volume of a can. It turns out to be pi r squared h. Now, pi r squared h also uses those 3 variables, which is perfect. And so we're ready to kind of move on to finishing this problem. Now, when you finish the problem, you're ultimately going to do the derivative. But it turns out that one of our numbers, it's special. It's special because it's not changing. Now, when a number's not changing, that means that it doesn't have a rate. And so you take numbers that are not changing, like 5 for this problem, and you actually plug it into your formula, ready? Pre-derivative. Pre-derivative means before you turn your formula into a rate formula. You see, before I do the derivative, I'm going to plug in numbers, like in this problem, 5, that do not have a rate, that are static. And so you see here that I actually get rid of one of my variables. I get rid of r. My formula also changes, in this case to be 25 pi h. But now, when I'm ready to finish this problem, that is to actually do the derivative, technically that's step 5, and do the derivative of these variables, I don't have to worry about my radius. I don't have to worry about my radius because it didn't have a rate. Let's do the derivative of volume with respect to time. That gives you dv dt. 25 pi, as we already discussed in the bubble problem, it's a coefficient. It doesn't change. Just bring it along. The derivative of h, that's right, dh dt. Now, this formula, this derivative that now relates the rates, obviously it contains the rates that we were working with in this problem. Particularly, you can see that it contains the volume rate. And so what we're going to do is we're going to substitute in here for dv dt negative 30. You can also see that it contains dh dt. That's the rate that I'm trying to find. I don't want to substitute anything in there. I'm going to actually be solving for dh dt. Divide both sides by 25 pi. And you have found dh dt. Now, remember, I am going to be a little picky about how you label these rates. So when you say negative 0.38, I want you to label that as the change in the height. That is centimeters per second. So it's kind of like the water level, not kind of, it is that the water level is dropping by negative 0.38 centimeters every second if you're losing negative 30 mils every second. Now, are you starting to get a little bit more of the idea of a related rates problem? You're still young at this, but I just kind of want to summarize that we definitely want to start to get in the habit of organizing what we're given, starting to get maybe a little bit more comfortable thinking about dt. Remember, dt is just represents the change in time, and of course turns your numbers, your labels into rates. And of course, we need a formula that's going to use those variables. But we have this interesting step in this problem. I just want to kind of come back to that one more time. If you have a number that does not change, that doesn't have a rate, you actually want to plug that in pre-derivative. You might even want to write something like that down, that you want to plug in those types of numbers pre-derivative, because you don't want to take the derivative of a variable that has no rate. Now, once you do that correctly, you can take the derivative with respect to time. It's just going to give you that dt symbol, and we can plug in and solve for what we're trying to find. In the next video, we'll certainly pick up with the next example, but for now, that's a wrap.